Okay, good morning and good evening, everybody. And first, I would like to thank Professor Warburton for organizing this series of seminars for the international community of quantum annealing. It's very important, I believe. So let me share the screen. So I will talk today about quantum optimization or quantum annealing of a continuous variable function in one dimension with rugged energy landscape. I'm Hidetoshi Nishimori from Tokyo Institute of Technology. And this is joint work with Patrick Coe, and the paper has already been published in Physical Review A, written here. And this work is funded by NEDU. So let's define the problem. It's a one-dimensional continuous variable x function, v of x, and it is defined by this harmonic term and the oscillating cosine term on top of it. So the overall structure is a harmonic potential, but there are a lot of minima and maxima by this cosine term. And the height of the potential is denoted as h0 and width is w0. And indeed, this is a famous one-dimensional version of the famous Rastrigan function, which is a standard benchmarking function in the field of mathematical optimization for continuous variable problems. So let's try to see what quantum annealing can do on this standard problem. And indeed, this problem was already studied almost 40 years ago by Shinomoto and Kabashima in the context of classical simulated annealing. And they analyzed the performance of simulated annealing by a coarse graining approximation. That is, they assumed that a particle can exist only in those discrete positions corresponding to local minima. And they assumed that the particle can go over the barrier to the next local minimum by the usual Boltzmann factor e to the minus h0 divided by the temperature. And they wrote a hopping equation between those discrete places, and they took the continuous limit by taking the zero limit of this width. And they solved the resulting differential equation to conclude that the optimal annealing schedule, the temperature as a function of time, is proportional to the inverse of the log of time. And correspondingly, the residual energy, which is the error of the algorithm, is proportional to the log inverse of the log of time. And this is a very slow process. It is natural because at very low temperatures at the end of the process, the particle around here should go over the barrier, which is exponentially hard for low temperature. So this is a result by an approximation theory 40 years ago. And in 2005, Stella, Santron, Tosati, and Trieste analyzed the same problem under the context of quantum annealing. And they adopted a very similar approximation. That is, once again, they assumed that the particle can exist only in one of those minima, local minima. And they assumed that the particle can tunnel through the barrier to the neighboring position. And again, they took the continuous limit of the width and solved the resulting continuous differential equation. And their conclusion is that the residual energy decreases as the inverse of time. So this polynomial decrease is exponentially faster than the log decrease. So it's impressive. So these are known results. And our goal is to see, is missing here, sorry, to see if those approximations are reliable. And our answer is that yes, qualitatively, but no, quantitatively. You will see what I mean by these statements. So let's describe the method in some detail for the quantum case first. We solve the time-dependent Schrödinger equation in which the mass of the particle m of t changes as a function of time. And the simplest annealing schedule is a linear schedule for the increase of mass from initial value mi to the final value mf in the time t. And the small mass of m corresponds to a large h bar, as you see here. So initially, the system is quantum mechanical. And at the end of the process, mf, the final mass, is very large, which corresponds to a small value of h bar. So the system is classical. So this is a process from the quantum region to the classical region in the spirit of quantum annealing. And we measure the residual energy as a function of the annealing time t. The residual energy is defined as the difference between the obtained energy at the end of the process and the ground state energy at the final mass mf. So if r is 0, it is best. The smaller the r is, the better. So we solve the time-dependent Schrödinger equation very precisely. And for a fair comparison of quantum annealing and simulated annealing, we took the energy as the measure. For relatively large energy, in this case 0.6, the probability distribution of the quantum stationary state wave function looks like this, which spans over many local minima. And at the same internal energy 0.6, the classical Boltzmann distribution has this distribution. Apart from some small structure, both of those probability distributions encompass many minima. And we decrease the energy, or we increase the mass in the quantum case, and we decrease the temperature in the classical case in time t in the first stage of annealing to reach the intermediate state in which the energy, 0.1, is about half of the barrier height. So at this intermediate state, the probability distribution for the quantum case has a very large value at the central valley, but the classical distribution has significant values at other local minima. And in stage 2, we further decrease the energy to 0.015 or 0.016. And at this value of the energy, the quantum distribution almost exclusively exists only in the central valley, whereas the classical probability distribution has small but non-negligible values at nearby local minima. And we further decrease the energy in stage 3. So we decrease the temperature or increase the mass in 3 stages. So let's see the result for the quantum case. As you see here, the value of the residual energy as a function of the annealing time in log-log scale. In all stages, the energy, the residual energy decreases in proportion to T inverse squared. So this is in agreement with the theory of Suzuki and Okada who employed an asymptotic expansion from the adiabatic limit. And this is, however, different from the coarse graining approximation of Stella Santorsotti, who predicted that the residual energy would decrease T inverse. And let's see what happens actually dynamically as a function of time. So for instance, in stage 2, at a relatively short annealing time 320, this red curve denotes the probability distribution. And this thin green black curve is the potential. And this light green indicates the instantaneous energy. So as the energy decreases, the probability at the central valley increases. And there are two very interesting facts in this video. First, the energy is lower than the barrier height. So the increase of the probability at the central valley is caused only by quantum tunneling, not the process that drives the particle over the barrier, but through the barrier. So this is a very clear, explicit manifestation of the quantum tunneling effect in this model. And second, look at this blue curve, which indicates the probability current as a function of time. So it oscillates. For instance, at this instant, this current for positive x is negative, which means that the probability goes toward the center. And this probability of positive probability for negative x means that the probability flows toward the center. So it is favorable. But it oscillates as a function of time. As you see, at this instant, the probability for positive x is positive, which means the probability flows away from the center. And the same is true for this part. So the short annealing time is not very effective because the probability goes back and forth by tunneling. And this problem is mitigated for a larger annealing time, 320, 30 to 50. As you see, it is relatively it is relatively monotonic. You see, this negative probability means that probability goes toward the center and toward the center from the left as well. For the largest annealing time, it is very monotonic. But it is still non-adiabatic in the sense that in the adiabatic process, the current should be 0. And the probability increase at the central valley means that the probability tunnels through the barrier. And in stage 2, it is very interesting to see the behavior of those curves for very short annealing time, 320. The probability that center increases eventually, but it is very non-monotonic. Anyway, at a later stage, when the energy is lower than the barrier height, quantum tunneling effect takes place very explicitly. And for a longer annealing time, 30 to 50, it is relatively stationary because the current is close to 0. And in stage 3, at a very low value of the energy, for relatively large value of the annealing time, the probability almost exclusively exists only in the central valley. But within the central valley, the behavior is not necessarily monotonic. It oscillates a little bit. So this is how the particle moves around, in particular by quantum tunneling effect. So We also tried another annealing schedule by choosing nonlinear function for the increase of the mass. As I said, in the linear schedule, the mass increases from mi to mf monotonically this way. But the theory called the boundary cancellation method predicts that if we impose vanishing derivatives initially and finally, then the rate of decrease of the residual energy is enhanced to the t to the fourth inverse. And if we further impose the condition that also the second derivatives at the initial and final times vanish, then the rate of decrease is further accelerated to t to the sixth inverse. And we tested this prediction numerically. And we confirmed these predictions are correct in stages 1 and 3, but not in stage 2. So the rate of decrease is much quicker than predicted in stage 2, probably because for this annealing time is still short for this theory to apply. And we can see once again what happens in the probability current by adopting those nonlinear schedules. As I said, for the linear schedule in stage 1, the probability current oscillates. The current becomes positive and negative, and the probability increases and decreases as a function of time, which is a very inefficient process for annealing. But if we adopt an F2 schedule in which the first derivatives at the initial and final times are 0, then you see, even with the same annealing time, 320, short annealing time, the current becomes monotonic in the sense that for positive x, the current is negative, meaning that probability flows into the center. And the same is true for negative x. So those boundary cancellation method leads the system more efficiently by making the probability current monotonic, which can be seen visually this way. And the same is true for higher order non-monotonicity. It's negative here and it's positive here. So these are the main results. And let's see what happens for the classical case. If we take this annealing schedule predicted optimal by Shinomoto and Kawashima, we found that the residual energy decreases log to the inverse of some power. And this power, in this case 0.74, depends upon the stage, around 1. Not exactly 1. Probably because if the final temperature is much lower than these values, this -1 may be recovered, but we couldn't confirm it numerically because it takes a very long time. And if we decrease the temperature more quickly, like this, it's much quicker than the logarithmic decrease. And if we take the annealing step larger than the barrier width, in this case 1, the next position x t plus 1 is chosen to be xt plus delta t, where delta t is chosen between minus s to plus s uniformly. And if we choose s equal to 0.1, then the particle hops between local minima, ignoring the energy barrier. So this is a quasi-global search. And by this quasi-global search, we found numerically that the rate of the decrease is t inverse, which is much faster than the inverse log law in the previous page. So this is natural because the particle doesn't feel the energy barrier. So this is essentially a search process for the envelope, the harmonic oscillator. So it is quick. So it may be one of the fastest classical algorithms because it doesn't see the structure. But still, you see, this power decay, inverse power decay, is slower than this square inverse in the quantum case. So there is a possibility that quantum annealing is the fastest algorithms among all, including best classical algorithms, but we couldn't prove it rigorously. This is a challenge, very interesting problem, I believe. So to conclude, we found that quantum annealing decreases the energy as a function of t in the low t square inverse. And nonlinear schedule further accelerates the decrease to any power of t, which is much faster than the local search in the classical case. But even if we adopt a quasi-global search in the classical process, quantum annealing is faster. And we also visually confirmed the process of quantum tunneling. Thank you very much for your attention.
Great, thank you very much, Professor Nishimori. Round of applause on behalf of everyone in the audience, I'm sure. And I'm very happy to open up this presentation for questions. If anybody has a question, either speak up or raise your hand. The Zoom.
I can show you the first page for reference if you're interested.
Here. Very useful. Maybe I'll have a question then. So I like this idea of changing the mass during the anneal, whereas the conventional approach is to change the transverse field. Are those two approaches exactly equivalent, or is there some detail that somehow is lost when you?
There is no direct correspondence. It is intuitively likely that they are similar, but I have no rigorous or even approximate theory to connect this way to increase the mass to the way where we decrease the transverse field.
So have you looked at changing the transverse field for this rastegram function that you've been looking at, or have you only focused on changing
Well, actually, I'm doing that study now. I can't review the details, but okay, I'm doing, and we are getting a very interesting result, which I may be able to announce in a few months of time.
I'm looking forward to hearing that result already. Good, good. And if I may ask another question, you were talking about, you mentioned in passing, I guess, that this probability current should be essentially zero in the adiabatic limit. And maybe there's something I'm not quite understanding there. So that's certainly true in the case of this rastegram potential, where your minimum is always at x equals 0. But in general, in a quantum annealing process, your minimum may shift from one value of x to another value of x. In this case, you need to somehow have a probability current, even though you want to shift from one to the other adiabatically. Am I misunderstanding something, or how do I think about that?
In the adiabatic limit, in the real limit, the current should vanish, I believe. Infinitesimally small, at least. And it's a matter of the distance between the actual, the theoretical adiabatic limit and actual adiabatic approximation. It is very small if the process is close to the adiabatic limit, but it may not be 0 exactly if you don't take the real limit of t infinity.
Sure, okay.
So as you see in this graph, it is small for a large value of t.
There's a question from Glenn. Go ahead, Glenn.
Yeah. Yes, thank you very much for the talk. So I had actually a question about the boundary cancellation. So it seems that with boundary cancellation, you can go, I mean, you said you can go beyond this t to the -2, right?
Yeah, right.
So, but then in the end, what you care about comparing is just this t to the -2 to the t to the -1 you get in the classical case, right?
Yes.
Why? So why are you not putting? Wouldn't it be? I mean, with quantum you can get even better acceleration. Why would I want to compare instead the t to the -2 with?
Oh well, even the worst power in the quantum case is better than the classical case. That's what I wanted to say here.
Okay, I get it. And
Okay.
in the classical case, there is no effect similar as the boundary cancellation that allows to do things like that with the T schedule. Is this true?
I don't know. Actually, I don't know. As I said, it's unlikely that a better algorithm exists in the classical case beyond this quasi-global search. It's a very simple harmonic potential. So I don't have a proof, but it is very likely that any schedule for the classical case would not supersede this inverse power law. I believe, but I cannot prove it.
Okay. Yeah, thank you.
There's a question also from Matthias Werner. Matthias, go ahead.
Hey, yeah, thank you for the very interesting talk. I have two questions actually. And one is about the various annealing schedules that you tried. Could you please again show that slide? Exactly this one. On the plot to the very left, it seems like a little bit as that in the if you basically increase the number of derivatives that you set to 0, that eventually this would turn to like some sort of a step function, right?
In the end, it may be, yeah.
Yeah. How does it relate to like the adiabatic theorem or the like the conditions for adiabatic annealing, since the step function would be like very non-smooth and yeah.
Well, I have no way to answer that question. Well, it's a difficult question.
Okay.
I'm sorry, I cannot answer this question. I don't have an answer.
Yeah, no worries.
But this theory is very reliable, although it is not mathematically rigorous, I should say. It is very reliable, I believe. This is the asymptotic expansion from the adiabatic limit, T infinity limit, expansion in terms of T inverse. So if you take the limit that all derivatives becomes 0, then it may be a step function, or it may be a function with some essential singularity here and there. Well, so I'm not sure.
Okay.
This limit starts to look a bit like QA-OA. And there are
QA, yeah, maybe, yeah.
There's some interesting work on the overlap between QA-OA and quantum annealing, which is of interest to us. So I'll just add that comment if I may.
Sure. Yeah, well, thank you. And yeah, another question I had actually, if I may, in the potential that you're optimizing, it seems like the local minima are all of the same width, more or less, right? Are you aware of work that looks into a loss function like that, but with where the local minima are of different width? So some of them are wider than others?
Yeah, that's an interesting possibility. Yes. We couldn't go into that direction because the computation is very heavy for that case. But actually, Steras and Trossati gave an argument for that, and they didn't draw a very definite conclusion, but they mentioned that problem as well. I don't remember, I confess, very precisely, but that can be done. But in that case, if there is some randomness, localization problem arises, which may lead to a very difficult problem, even for quantum annealing. But that's an interesting problem. Yes, I agree.
All right. Yeah, that was my questions. Thank you very much.
Thank you.
Do we have any more questions for Hidetoshi? Okay, if not, let's I'll thank Professor Nishimori again on behalf of the audience. Thank you very much. Very interesting talk. And
Thank
you everyone for attending. And we're looking forward to hearing the next presentation in 2 weeks' time from Glenn Lebain. Thank you very much, and enjoy the rest of your days, everyone. Bye-bye.
Thank you. Bye-bye.
Thank you very much. Goodbye.
Bye bye.
Bye.